Alright, welcome everyone to the next video in this series, and in this lesson we will look at pod routing. Now in the previous lesson we looked at pod networking, which was the process of creating a network interface for the pod, and we looked at the role the CNI plays in that process, including other components such as the container runtime and kubelet. Now in this lesson we're going to talk about pod routing, which is the process of moving packets in and out of your network so that your pods can communicate with other pods in the cluster as well as other workloads in your broader environment. Now, in this lesson, we're going to specifically look at pod-to-pod communication in a Kubernetes cluster. And for that, we have two scenarios. The first scenario is pod-to-pod communication within the same node, as in pods scheduled in the same node. And the second scenario here is pod-to-pod communication between pods in different nodes. Okay? So let's get into it. Okay, so first I'm going to go through a couple of diagrams to level set here. The first diagram is for the first scenario, which is pod-to-pod communication for pods scheduled on the same node. So in this diagram here, we have cluster node A. And in cluster node A, we have the host network namespace, which is basically the network namespace that belongs to the node. And we also have a couple of pods, pod 1 and pod 2. And you can see that these pods have their own namespaces as well. Okay. And we looked at this during the previous lesson. Now, the CNI configures the default routes for the pods in this node. And you can see that in both cases, the default routes are the same. They are pointing towards the ETH0 interface. And what that means is if pod 1, for example, has to communicate with pod 2, as indicated by this packet, it's going to pump that traffic out the ETH0 interface. Okay. Now that traffic then reaches the host network namespace. And while in the host network namespace, the host is going to perform a route lookup to determine how this packet should be forwarded. Okay. So for example, here, if you look at the second pod, it has an IP address of 192.168.93.202. All right. So the destination IP would be 202. And as the host does a route lookup to determine where that packet should be forwarded, the route table is going to reveal that the packet should be sent to this particular Kali interface, which is one end of the V8 pair for this particular pod. So once the packet gets forwarded, since it's a V8 pair, this packet is then going to reach the destination pod. Okay. Now, if you look at the return path, so communication is always two ways. There's a return path as well, although in this diagram, I've only shown one direction. But if you look at the return path, the destination IP when this pod sends the return packet would be of pod 1, which is 192.168.93.201. And when the host does a route lookup for that IP, it's going to reveal this particular Kali interface, which is this end of the V8 pair that belongs to pod 1. The traffic gets forwarded and it will reach pod 1 via this interface. Okay. So that's how pod-to-pod communication within the same node takes place. And it's Calico Felix, which is a component within Calico that programs the routing table in such a manner as and when pods are provisioned or deployed to this particular node. Okay. So that's a function of a CNI as well. All right, so that's the first scenario. Next, let's look at the second scenario, which is pod-to-pod communication between pods in two different nodes. Okay, it's very similar, but there are some distinctions as well. Now, if you recall in the IPAM lesson, we looked at how Calico takes the IP address block and breaks it into smaller blocks and allocates those blocks to individual nodes, right? What Calico then does is for IPAM blocks that it has allocated for nodes, it programs the routing table as well in an aggregated manner. And let me explain what that means. So let's take this scenario. So we have two pods in two different nodes over here. So pod 1 is the same pod we looked at previously. It has an IP of 93.201. And if you look at pod 2 here, this one has an IP address of 112.197. Okay. And it's a /32 a mask, which means these are host IPs. Now, let's say that this pod wants to communicate with this pod. So it sends out a packet with the destination IP of the remote pod. And this packet lands in the host network namespace. So the host network namespace does a route lookup for the destination IP. And this route lookup is going to reveal that if you want to reach this pod IP, you send packets to 172.18.0.3. So if you want to reach any IP that belong to this CIDR block, you send that to 172.18.0.3, which is the ETH0 interface of that particular cluster node, right? So where did Calico get this CIDR block from? Well, this is a CIDR block that is allocated to this particular node. So any pod that comes up in this node is going to have an IP that belongs to this CIDR block, right? So Calico need not program routes as and when pods come up in remote nodes, because any pod, provided that you don't exceed or exhaust the IPs that are available, will belong to this particular block. Now, if you exhaust the IP, so this block, being a /26 will provide you about 64 IPs. And let's say you exhaust it. Let's say you deploy 65 pods for this particular node. So what IPAM does is it will then allocate a new block for that node, in which case Calico Felix here will program the route for that new block as well, pointing to the respective node it was assigned to, right? So that's how the prefixes are programmed for IPAM blocks that are allocated to different nodes, okay? So in this particular example, packet lands to the host network namespace, a route lookup is done that reveals that for this particular block, forward traffic to this ETH0 interface, in which case this packet then lands at the host network namespace. This node does a route lookup for that IP, and that lookup reveals that for this particular IP, which is 112.197, you forward traffic to this particular Cali interface, and then that packet eventually reaches the pod that it belongs to or is destined to, okay, in this case. Now, looking at this diagram, I think I should ideally, depicted a packet in the host network namespace as well, but consider that to be the case. I'll modify this diagram in the final version of it. All right, so with that in mind, let's go to the lab setup here and look at how pod networking happens under the hood. So we looked at the two scenarios here. Now I've already provisioned the lab in my environment. If you've cloned the repo, there is a folder called container lab, in which we have another folder called pod-routing, which has all the files that belong to this particular lab. So if I do a tree-l1, these are the files in this lab. It's very similar to the previous labs, and we have a video that does a detailed walkthrough of the labs. So if you want to understand how these labs are structured and how we provision the environment, please have a look at that video. But very quickly, in this particular lab, we have a container lab topology, which is this one over here. Very similar to the previous labs, we are deploying a kind cluster. And if I look at the configuration of that particular cluster, we're deploying a 3-node cluster with no CNI, since the deploy script will install Calico CNI. And the pod subnet is 192.168.0.60/16. And that's why you see those 192.168 IPs in the pods that we deploy. Now, there is a folder called tools. So if I do a cd tools, and in this folder, I have a couple of manifests here, multi-tool 1 and 2. Just ignore this one for now. And these manifests are basically for daemon sets that we deploy as part of this lab to verify the routing between pods, and we will look at that in detail as we go through the lab, right? So just bear in mind that we are deploying a couple of daemon sets that will help us validate pod-to-pod routing, okay? All right, so with that in mind, let's validate the lab container lab topology. So we have a 3-node cluster here, and these are the IP addresses of the cluster nodes, okay? And let's set up the kubeconfig file. So, as part of the lab, you deploy or run the deploy script, right? And the deploy script will spit out the kubeconfig file for the respective labs. So for this lab, we configure the kubeconfig file as an environment variable, and then we can do a kubectl get node for this particular cluster. Let me just expand my output here a bit. So if you look at the IP addresses of the node, they correspond with the ones that we see in the container lab topology as well, okay? Alrighty, so I think the important thing to bear in mind here is we will be using worker and worker 2 as the two nodes for which we will validate pod to pod routing. Okay, so worker 2 has an IP of 172.18.03, and worker here, which is essentially worker 1, has an IP of 172.18.01. So if I go back to my previous diagram here, we see that worker, or worker 1 rather, has 172.18.02, and worker 2 has 172.18.03, right? So those are two important IPs, which are IPs of the ETH0 interfaces that belong to the workers. Okay, so with that in mind, what we will do next is I'm going to do a kubectl get pods -o wide, and these are the daemon sets that we've deployed to this particular cluster. And if you're interested in looking at the manifest, you could just go to the tools folder, and if you do a cat, it's a very simple manifest for a multi-tool pod in this case, and these pods will help us validate the network configuration. Okay, so let's get that output one more time. So if I look at the deployment of these pods, now these are daemon sets, right? So we have multi-tool 1 over here, which runs on all the 3 nodes, and we have multi-tool 2, which also runs on all the 3 nodes. Okay, so just bear that in mind. 3 pods in each of these daemon sets, and they run on each of the nodes. Okay. All right, so let's go through the first scenario, which is to examine pod-to-pod communication for pods within the same node. Now, if I look at this particular pod, which is this one over here, this pod is deployed in the worker node, worker 1 node, this one over here, right? So in this step, what I'm going to do is I'm going to exec into that particular pod. So essentially, in our first scenario, right now, I'm inside pod 1, if you look at that first diagram, okay? So from there, if I do a IP ADDR, I can, verify the IP of that pod. It's 93.201. And if you look at the diagram, it's 93.201. Now just bear in mind that your outputs are going to be different, right? These settings are dynamic, and it's not deterministic. So your outputs are different. In the diagrams, I've indicated the IPs to be what they are in my particular environment so that it's easy for me to go through this step by step. But just bear in mind that in your environment, these outputs are going to be different, right? Okay, so we've verified the IP of that pod. And if I do an IP route, we're able to see the default route as well, which points to the link local address for this particular ETH0 interface. Okay, so next what I'm going to do is I'm going to initiate a continuous ping from this pod to the pod scheduled in the same node, right? So let me go ahead and start that ping. And I can look at the output of this ping if I cat this particular log file. And as you can see, the ping is successful. So what we did was from pod 1, we pinged pod 2. So we're pinging 192.168.93.201. And that basically is, so 93.201 here. And we're basically pinging 192.168.93.202. So on the same node for multi-tool 1, we're pinging multi-tool 2. All right. And that ping is successful. So basically pod-to-pod communication within the same node is working. Now, in the ping, you're going to notice that there is a TTL of 63. So when a packet comes out of the pod, it has a TTL of 64. And each routing hop is going to reduce the TTL by 1. So this packet passes through 1 routing hop. So it's going to have a TTL of 63 in the response, ICMP response. Okay. All right. So what I'm going to do next is I'm going to exit from this particular pod. All right. And then we are going to get into the worker node, which is worker 1 essentially, right? So we've now come out of the pod, and right now I am in the worker node. And if in the worker node, if I do a route, IP route and grep for the IP of the second pod, we're going to see that that route points to this particular interface. And if you look at this interface, it is the host end of the virtual Ethernet pair. So this particular interface over here. Let me expand this output a bit. So we are looking at this particular interface over here. So basically, from the host side, if it receives a packet that is destined to 192.168.93.202, it's going to forward that packet to this particular end of the veth pair. All right. So that's how essentially routing happens, on the host side of things. Okay. All right. So next, what we're going to do is let's exit from the host and let's exec into the second pod. So we're going to now exec into the multi-tool pod on the same node, right? So now I'm inside the multi-tool pod. And from the pod, we're going to run a TCP dump, right? So when you run a TCP dump, you're going to see that 201 is pinging 202. And you see the ICMP requests and ICMP responses as well, right? So then 202 gets back to 201, and all of this back and forth is successful. I think the important thing for you to note here is that the pods can see each other's IP. So there is no network address translation, which is a very important requirement and principle in Kubernetes pod-to-pod communication. The CNI has to ensure that pods are able to communicate with other pods in the same cluster without network address translation. And this TCP dump confirms that, right? So pod 2 in this case can see the source IP of pod 1. All right. So that's basically the first scenario. So let's exit from this, and now let's go to the second scenario, which is pod-to-pod communication for pods scheduled in different nodes, right? So for this second scenario, we're going to exec into the same multi-tool one pod, right, in node 1. If I go to this diagram, I've exec into this pod, and we're going to initiate another continuous ping. So let me copy this command, and I'm just going to change this log file, let's say different node ping. All right, and let's initiate that ping. And if we do a cat file for that particular log file, we can see that the pings are successful. And unlike the ping in the previous case, you see that this ping response, or the ICMP responses, have a TTL of 62. And why is that? That's because this particular packet had to go through two routing hops. So first, it came out with the TTL of 64. It went through the first routing hop, which reduces its TTL by 1. And then when it went to the second routing, or the second node rather, that reduces the TTL by 1 as well. So the TTL is 62 since it had to jump through two routing hops. Okay, so that's a good way of looking at, whether a particular pod is scheduled in one node or a different node in the cluster. Now, regardless of how large your cluster is, now your cluster could have hundreds of nodes. Pod routing tends to be efficient, right? So in most cases, it's only going to jump through two routing hops to reach pods in the cluster. And that's actually provided that the nodes are in the same subnet. In a Kubernetes cluster, you could have nodes that are in different subnets as well, in which case you would have to jump through multiple hoops, right? And that's where the conversation about overlay networks come into play as well. And we have a separate video that explores that. In this lesson, you got to bear in mind that these nodes are scheduled, or deployed rather, in the same subnet. So between the nodes for communication, it doesn't have to go through a layer 3 routing hop, or it doesn't have to go through a router for packets between these nodes, given that they are in the same subnet. All right. Okay, so with that in mind, let me exit from this particular node. We saw the ping responses, they are successful. And I'm gonna now exec into the host node, right? So if we look at the second scenario, right now I'm on cluster node A, this particular host node. Okay, so let me now do a IP route get for the IP of the destination pod. And as I get the output here, I can see that for this particular destination IP, the next hop is 172.18.0.3, right? So if I go back to the diagram, as this packet comes to the host network namespace, the next hop is 172.18.0.3, which is the ETH0 interface of cluster node B in this particular diagram over here, right? So ETH0 interface of cluster node B. So essentially, when this node receives the packet, it's going to send it out of its ETH0 interface to the ETH0 interface of the cluster node to which this pod belongs. All right. Now, what I can also do is just to show you. So this is an IP route get. If I do an IP route and if I grep for 192.168.112.192, you can see that there is a /26 route. And this is what we call the aggregate route. So Calico is not going to program individual pod IPs for pods that are scheduled on peer nodes. Instead, you're going to see /26 routes, or rather routes that align with the block size that you've configured for your cluster, right? So if I look at the entire routing table in this particular working node, or worker node rather, for pods that are scheduled on the same node, you're going to see host routes, as in specific routes, pointing to the respective Kali interfaces or the host side of the virtual Ethernet pair. However, you're going to see /26 prefixes for routes pointing to pods on peer nodes of the cluster. All right, and that's how it ensures efficient routing. And that way you don't have to program routes as and when pods come up or churn on those peer nodes, and you minimize the number of entries in the routing table as well with this aggregated approach. Okay. All right, so we looked at the routing table on the source node. Let's exit from this. And now what we're doing is execing into the destination node. And on the destination node, if I do an IP route for the destination pod, you're going to see this output that points to the Kali interface. On the destination node, we see that the route points to this particular interface over here, right? Which is the host end of the virtual Ethernet pair that belongs to the destination pod, all right? And similar to the previous case, if we exit from the destination node and exec into the destination pod, which is the multi-tool 1 pod on the second worker node, and if you do a TCP dump, you can see the ICMP requests from the multi-tool 1 pod on worker 1, and you can see the responses sent by this particular pod as well. And the important thing again here is that this pod sees the source IP of the pod that initiated those ICMP requests, right? So there's no NAT that takes place when pods in different nodes communicate as well, similar to the first scenario, right? All right, so that's how you can validate pod-to-pod communication. It's very useful to know how this works under the hood. It's possible that you might find yourself in scenarios where you have to troubleshoot pod-to-pod communication. One of the first things I do is to ensure that all the routing is in place and get that out of the way, right? You could also do ICMP requests such as this and packet captures such as this to verify that a given pod can send and receive traffic within the cluster. All right. Okay, so so in this lesson we looked at pod-to-pod communication for workloads that are deployed inside the cluster. And in subsequent lessons, we will look at some other scenarios as well, such as communication for services or from sources outside the cluster, as well as how overlay network works in Kubernetes and why you may want to deploy overlay networks. So with that, thanks for watching. Bye for now, and have a good rest of the day. I'll see you in the next one.